right, welcome to the Friday afternoon colloquium. Our speaker today is our own Dr. Fred Ringwald. So Fred began his illustrious career in academia at Northwestern University. He got his PhD from Dartmouth. He's held positions at Florida Institute of Technology, Penn State. He worked at the Atlas Planetarium. He was also had a postdoc at Keele University in jolly old England, and I think a postdoc at U of Arizona Space Science Institute.
You forgot to work with the Klingons, the Gorons, and the Romulans.
Yes, also that. So Fred has been a professor here since 2000. Basically, he's the heroic leader of our astronomy program, and today he's going to tell us something about James Webb, Nancy Grace Rubin Space Telescope, and also Hubble Space Telescope and Vera Rubin Observatory. So Fred, take it away.
Astrophysics in the coming decades. Astro 2020 is the new decadal survey on astronomy and astrophysics, sponsored by the National Academy of Sciences. It was just published a few weeks ago. Typically, the decadal survey is actually published a couple of years after the beginning of the decade, or rather the 0 year of the decade. These decadal surveys have been carried out every 10 years since 1960. And the US Congress likes this, as it makes astronomers look like we have our act together. Lack of similar surveys in physics aided the cancellation of the superconducting supercollider, which was designed to reach 3 times higher energy than the Large Hadron Collider, but largely because they really did not do such a great job of presenting to the public why this was important and worth 11 going on $14 billion. Congress pulled the plug in October 1993, and it is lucky that the Higgs boson happened to be in the third of the parameter volume that was capable of searching for the Higgs boson. So finding the Higgs boson, that the Large Hadron Collider did find the Higgs boson, was basically beating 1 to 3 odds. In other words, about twice as dangerous as playing Russian roulette. The planetary science, heliophysics, formerly solar and space physics, and earth science fields have all adopted decadal surveys since 2000, since they have seen the good effect this has on funding. The point is that most major initiatives in astronomy and astrophysics since 1960 began in these decadal surveys. The 1960 decadal survey on astronomy and astrophysics, published in 1964, they usually come out a couple or 2 to 4 years after they're actually held. Top priority was the 4-meter telescope at Kitt Peak National Observatory, shown here, which is in Arizona, completed in 1970, and the 4-meter telescope at Cerro Tololo Inter-American Observatory in Chile, completed in 1973. Also recommended were many of the 1 and 2-meter telescopes shown here at both observatories. These are national observatories. In 1960, astronomy was very much an old boy network, and the only telescope comparable in size to these was the 200-inch telescope at Mount Palomar, 5 meters in aperture, the world's largest telescope from 1948 to 1991, when the Keck 1 telescope, twice as big, came into operation. The point is that in 1960, if you wanted telescope time on the biggest and best telescope in the world, you had to either be on the faculty of Caltech or know somebody who was, or Carnegie, or the staff of Carnegie Research Institution, or know somebody who was. So the idea of building 2 telescopes comparable in size, 4-meter apertures, and comparable in quality and capability, that any astronomer with a PhD could apply for telescope time on, and the proposals would be selected on the basis of scientific merit only. And I believe that because I've served on these committees, and I think they usually do a pretty good job. And so they have been very productive ever since. Vera Rubin, for example, discovered dark matter, largely with observations she took with the 4-meter. And here's a picture from Dartmouth's observatory across the mountain. So I know both observatories quite well. Another reason Cerro is, of course, in Chile, and people are friendly in Chile, and they don't get mad at you if you don't speak the language like in some countries like France. The problem is they don't know English. So, and you are a very long way from home. So therefore, yet another good reason why Spanish is a very good language for astronomers to know. And here is the view of the Kitt Peak National Observatory at sunrise from Dartmouth's observatory, which is across the mountain. So the 1960 survey recommended the construction of the Kitt Peak 4-meter and Cerro 4-meter telescopes. And they've been very successful ever since. For the 1970 decadal survey, published in 1972, top priority was what was called at the time the Large Space Telescope. In 1983, this was renamed Hubble Space Telescope. Hubble is a large observatory-class telescope installed at Titanic expense in low Earth orbit above Earth's atmosphere. It's not very deep in space, and it doesn't fly from planet to planet like a space probe. We have those too. Hubble is just a large observatory-class telescope delivered by space shuttle into Earth orbit above enough of the atmosphere, 99.999% of the atmosphere. So it sees much better than a telescope on the surface of Earth, a ground-based telescope, as they call that, as opposed to a space telescope like Hubble. Hubble's above Earth's atmosphere was launched by a space shuttle in 1990. NASA wants to keep Hubble operational after 2030. It had 5 servicing missions by the space shuttle, the last one of which was in 2009, but the space shuttle has been retired. Nevertheless, NASA wants to keep Hubble operational after 2030 because of its unique ability to observe ultraviolet radiation. The new one, which you may have heard about in the news, James Webb Space Telescope, is actually mainly for infrared. It does have a little bit of visible light capability, but no ultraviolet capability. So James Webb Space Telescope, the new one, really is not a replacement for Hubble. It's a successor, but not really a replacement in that there's substantial things Hubble can still do. Observing, getting images and spectra in ultraviolet radiation that James Webb cannot do at all. So NASA wants to keep it going because there is much astrophysics to be learned in the ultraviolet. You may wonder why do this, why put a telescope in space, a 2.5 meter telescope like Hubble. On the ground, on a ground-based observatory, cost about $5 million. Hubble Space Telescope cost $2.5 billion. So why spend 500 times more on a telescope of the same size and presumably the same capability? The answer is, it's not the same capability. Hubble is above the obscuring effects of the Earth's atmosphere caused by twinkling of the Earth's atmosphere. When you look out at stars, they appear to shimmer and twinkle in brightness. The nursery rhyme, "Twinkle, twinkle, little star, I know exactly what you are." And if you wonder how I know, Carl Sagan told me so. The point is, this is very pretty. It's also called seeing, and the point is it blurs images. It's caused by turbulence in Earth's atmosphere. So if the image is bouncing around due to turbulence in Earth's atmosphere, it will get blurred very easily. The image on the left is an image taken of the Ring Nebula. It's an essentially perfect seeing, taken with Hubble Space Telescope above Earth's atmosphere. And look at all the detail you can see as you switched off the light so you can actually see the detail. You can see. And look how sharp and pinpoint focused the stars are. Look how big and blobby the stars are and how much of the detail you can't see in the image on the right. Because the image on the right is taken and not as good seeing, taken with Fresno State's humble little campus observatory on the lawn of the Botanic Planetarium. And actually not bad for a telescope at an essentially sea level site. The elevation here is about 300 feet, about 100 meters. It also cost 50,000 times less than the Hubble Space Telescope. and therefore is the telescope I mainly use in the observational astronomy class for students to teach them how to take pictures like this. Most of the students who take this class are physics majors and grad students who are smart. They know physics and math and quite a bit of computing, but most of them have never used a telescope before. So one's first telescope, right in front of you, where you're able to see and touch it, are big advantages. And that in it isn't bad. It's just not as good as a $2.5 billion instrument, which we probably should expect more from. Another reason to put a telescope in space is that Hubble observes ultraviolet and infrared radiation, not just visible light. Earth's atmosphere is transparent only to visible light. So this graphic, the various wavelengths, gamma ray, X-ray, ultraviolet, visible light. Notice that visible light is only a tiny portion, tiny range of wavelengths. Infrared, microwave, and radio. Visible light gets all the way to the surface of Earth, because Earth's surface is visible to visible light. Earth's surface is also visible to radio waves, so you can have radio telescopes, big radio receivers for astronomy on the surface of Earth, and conventional visible light telescopes on the surface of Earth. If you want to do infrared observing, infrared radiation is absorbed by carbon dioxide, water vapor in Earth's atmosphere. This is, of course, the greenhouse effect. And so if you want to observe infrared radiation from objects in space, you have to either put your telescope on a very tall mountain, or at longer wavelengths, put your telescope in an airliner, in an airplane. This is the Sophia Observatory, NASA's stratospheric observing for infrared astronomy. It's basically a telescope comparable in size to Hubble Space Telescope, an observatory-class telescope, looking out through a door cut in the fuselage of a retired 747 jetliner. And yes, it's gyro-stabilized and gimbaled, and the pilots make it a point to fly straight and level. And but best of all, if you got the budget for it, is to have an infrared telescope on an orbiting observatory, completely above the absorbing effects of the Earth's atmosphere. And the same thing goes for shorter wavelengths in visible light, like Hubble Space Telescope for ultraviolet, Chandra X-ray Observatory for X-rays, and Compton Gamma Ray Observatory for gamma rays. All this high energy radiation is blocked by ozone, is absorbed by ozone in the stratosphere of Earth's atmosphere. You can get one picture in a rocket with an X-ray detector or ultraviolet or gamma ray detector can fly up and take one picture if that's all you want. And there have been gamma ray observatories and ultraviolet observatories on high altitude balloons. The problem with that, of course, is getting the balloon back after you take the data. But satellites are expensive. So balloon-borne, rocket-borne, and airborne astronomy still do return significant data. But of course, what we would really like is to have a big budget and be able to afford spacecraft. Back when astronomers could observe only visible light, it was like watching television with only one channel. Now we got all the channels, from gamma rays to radio and everything in between. And we learn a lot faster and a lot better about the universe by being able to do this. The 1970 Decadal Survey also listed the Very Large Array Radio Observatory, not really near Socorro, New Mexico. They always say near Socorro, New Mexico. It's actually an hour away, in the middle of literally nowhere in New Mexico, completed in 1989. Of all the telescopes I have ever used, this one gave me the strongest sensation of, is this all for me? The answer is yes, but only till the end of the 8-hour shift. I have used Hubble Space Telescope, which is more expensive, but you don't actually see Hubble. It's an orbiting spacecraft. The only thing that you see is an office building on the campus of Johns Hopkins University in Baltimore, where they manage Hubble and where one or two of many people there are concerned with your project. so it doesn't have the visual effect on you as the Very Large Array. And it is still the top radio telescope in the world for centimeter wave radio. Many telescopes linked in phase together can have the same resolution as a much larger one. So if the two outermost radio telescopes are 27 kilometers apart, if you can phase the signals together in phase, usually with an accurate time signal from an atomic clock on site, you can synthesize images that are just as clear as if you had a radio telescope with an aperture 27 kilometers, which would be just a little expensive and difficult to make. It wouldn't be as sensitive because you don't have a dish that large, but you do have the resolution. You can see details clearly. And this is called an interferometer or an array. So what do you see? In visible light, this is an image of an active galaxy called Centaurus A. It's a big elliptical galaxy in the process of eating a smaller galaxy, smaller spiral galaxy, like the Milky Way, the one we're in. And notice the big old dust lane from the spiral galaxy is obscuring the central engine. It's thought that nearly all galaxies have big black holes in their centers. And when they have collisions like this and are active, they're active because lots of gas and sometimes whole stars are falling into the black holes in the middle. But it's obscured by the dust. Radio wavelengths, of course, have wavelengths. Radio waves have wavelengths much longer than the size of the dust grains, so dust is transparent to radio waves, and you can see right through it. You can see the central engine, the black hole, and you can also see two plumes of plasma radiating synchrotron radiation from relativistic electrons spiraling the magnetic field, apparently shooting out of the black hole. They probably aren't going out of the black hole. Things don't go out of black holes, they go into black holes. The presence of the black hole is probably warping space-time so much it's creating these jets and is shooting out perpendicular to the disk of gas that's, because notice, it's coinciding with the equatorial radius of the spiral galaxy. The physics of this is poorly understood. Whenever you hear anybody say relativistic electromagnetic tornado, what you should say is, why don't you just admit you don't know? We don't understand non-relativistic hydrodynamic tornadoes. And this is a relativistic magnetohydrodynamic tornado, two of them. Right, okay, great. The 2020 decadal survey, the one that was published just a few weeks ago, named the next generation very large array, the NGVLA, for the 2030. Since the VLA is now over 40 years old, and the antennae are showing signs of metal fatigue. A large dynamic structure out in the elements will have a limited lifetime. The big dish in Arecibo fell down in late 2020. It was over 50 years old. And in 1988, the 300-foot dish at Greenbank Observatory fell down. Precisely because of this. It's hard to maintain a large metal dynamic structure outdoors. So the next generation VLA was mentioned by the 2020 decadal survey. And again, this will be an interferometer with things spread out all over New Mexico and all over the United States, and from Hawaii to the Virgin Islands, and from Washington to New Hampshire, making a nice interferometer array so you can get not just deep images, but detailed images too. For the 1980 decadal survey, top priority was Chandra X-ray Observatory, the high-energy astrophysics answer to the Hubble Space Telescope. Basically comparable in capability to Hubble, but for X-rays. Hubble was delivered into Earth orbit with a very significant amount of aberration, half a wavelength of spherical aberration, a serious error in its optics, basically because of poor communications between the engineering teams that built Hubble. Therefore, necessitating an expensive and embarrassing trip by the space shuttle with astronauts to actually fix Hubble, and it's been fine ever since, but this should not have happened in the first place. So memories When Chandra was launched in 1999, memories were recent, memories were fresh about the problem with Hubble. So everybody looks all anxious. Is it going to work? Is it going to work? And then this picture was displayed of a supernova explosion, big cloud of gas thrown into space from a star that exploded, a nasty little neutron star remnant in the middle still there. And look, everybody is happy, smiling, happy. It works, it works. And it's been great ever since. Pictures, Chandra was the first X-ray observatory capable of getting images as detailed as those of visible light, ground-based visible light telescope. So it has discovered, for example, lots of black holes in other galaxies. I could go on and on. So visible light, what do you see with an X-ray telescope? So here's the visible light image of the active galaxy Centaurus A, like your eyes see. By the way, it does look just like that through the eyepiece of a telescope. I've looked at it. And the radio image looks like this. The X-ray image of the same object looks like this, with a jet of 100 million degree gas shooting out of the vicinity of the central engine of the black hole. Again, X-rays have such high energy, they go right through the dust. X-rays, of course, are well known for their ability to go right through the soft tissues of the human body, and therefore doctors have long been using them to take pictures of people's bones. Radio has long wavelengths, so it goes right through the dust too, unlike the visible light. So radio, you see plumes of plasma emitting synchrotron radiation. Here you actually see the $100 million gas carrying the plasma along. For 1990, top priority was Spitzer Space Telescope. It was launched in 2003. It was finally retired in 2020 for infrared. So here is Spitzer Space Telescope, as opposed to a ground-based telescope, or Hubble for visible light, or Chandra for X-rays. Spitzer was the last of the 4 shuttle-era great observatories, which included Hubble, Chandra, and Compton Gamma Ray Observatory, which was launched in 1991 by a space shuttle, finally retired in 2000. Compton Gamma Ray Observatory was the very first one that I worked on. Summer between my senior year as an undergrad and my first year of grad school, I wrote the very first mission plan for it, what to observe in a survey of the sky, because there'd never been such a sensitive gamma ray telescope before. So I had to do some literature research on what there was to see, and then what were the remaining areas of the sky. But Spitzer was the last of the 4 great observatories, shuttle-era great observatories, for Hubble for ultraviolet and visible, Chandra for X-ray, Compton gamma rays, Spitzer for infrared. The point is that thermal radiation of room temperature objects is most intense in the infrared. Therefore, infrared is useful for finding planets and maybe life. Also listed in the 1990 survey were the Gemini South and North 8-meter telescopes in Chile and Hawaii, completed in 2019 99 respectively. And here they are shown with their adaptive optics lasers turned on. Here are a bunch of infrared instruments taken with a bunch of infrared instruments taken with, and somebody is.
So hold on. Yeah, tell them to turn the mic off.
Somebody turned their mic off.
Everyone should have their mic off.
Okay. And okay, so what do you see? What do you see in infrared? You see, this is visible light of, again, a big galaxy eating a smaller galaxy, and the remains of a smaller galaxy obscuring the light from the central engine, the black hole that most of it is falling into. Radio, you see the plumes of plasma coming out of the central engine, the black hole that's riled up in the collision. X-rays, you see a plume of 100 million degree gas shooting out of the central engine. Infrared, you see the central engine itself. The central engine is the, in other words, the black hole in the center of these 2 galaxies merging together, is the brightest infrared source in the system. And infrared, of course, has long wavelengths, so it goes right through the dust. The wavelength of infrared radiation is larger than the grain size of the dust, so it goes right through it, unlike visible light. And also, you see some star clusters. towards the center, induced by the collision, formed recently, induced by the collision. For the 2000 decadal survey, top priority was James Webb Space Telescope. It cost $10 billion, the most expensive astronomical instrument of all time. Hubble Space Telescope, when it was launched in 1980, cost $2.5 billion, and at the time it was the most expensive scientific instrument of all time. The record holder is still the Large Hadron Collider in Switzerland at $13 billion. To give you an idea of how much that is, that's about as much as a civilian nuclear power plant or a U.S. Navy aircraft carrier without the planes and without the fleet of ships to go with it, just the aircraft carrier. So $10 billion, that's a lot. The budget for the whole of NASA space science since its inception has been fairly constant at $5 billion inflation-adjusted dollars since the inception of NASA in 1958. So this was a big thing. James Webb Space Telescope was essentially ate the entire budget of NASA space science for 2 years. It is therefore very big, too big to fail. It was launched on Christmas of 2021. It has now unfolded successfully and has reached its destination orbit at the Earth-Sun L2 neutral gravity point, about 1 million miles away from Earth, so therefore it cannot be serviced by space shuttle astronauts. One reason being the space shuttle was retired in 2011, and the other reason being it's 1 million miles out in space. The space shuttle flew maybe 400 miles high. Calibration is currently underway, with first science operations scheduled for June. James Webb Space Telescope has a 6.5 meter aperture. In other words, it would just fill up this room. Larger than Hubble's 2.4 meter aperture, about 8 feet across. James Webb is over 20 feet across. James Webb will also be cooled to 53 kelvins. You're not supposed to say degrees Kelvin, it's just 53 kelvins. And be far from Earth, because Earth is warm. Therefore radiating infrared radiation. Therefore a bright source of infrared radiation in the sky, and James Webb is designed to see faint infrared radiation. And also away from the sun. The L2 neutral gravity point is in back of the Earth, 1 million miles farther away from the sun, actually 900,000 miles farther away from the sun than the Earth is. At near-infrared wavelengths, it should therefore, James Webb should therefore be 100 times more sensitive than Hubble. James Webb also should be able to observe mid-infrared radiation, longer wavelengths. So what do you see with it? Well, remember the concept of look-back time. The speed of light is finite. The speed of light is not infinite. It takes time for light to get around the vast distances of the universe. So when you look deeply into the universe, it's like looking into a time machine. And Hubble has been used for that, to actually look deeply into the universe and work out the evolution of galaxies. What do you see when you look back all the way? And the answer is, you see the origin of the universe. You see the cosmic background radiation. Edwin Hubble, for whom Hubble Space Telescope is named, discovered in the 1920s that the universe is expanding, which had been predicted by general relativity 13 years earlier, although Einstein did not make a big deal of it because the idea that the universe could be expanding was too fantastic even for Einstein. But once Hubble could show it, Einstein came around, so the universe is expanding, therefore it's not difficult to imagine that the universe at one time in the distant past could have been much smaller. And by precise measurements of the expansion rate of the universe, this has been determined to be 13.8 billion years ago. The universe began in a hot, dead state 13.8 billion years ago in an event nowadays widely called the Big Bang. And this is the cosmic background radiation. It's a picture of the primordial fireball. It was radiated by the universe when the universe was about 400,000 years old, when the universe was about 400,000 years after the Big Bang, when the universe expanded and cooled enough to become transparent to light for the first time. So this is the first light radiated in the universe that we can detect. It's an actual picture of the primordial fireball. Since the universe has expanded by a factor of 1,500 since this early time, the visible light that this used to be has now been redshifted into a thin soup of microwaves that pervades the universe, pervades the sky. You can actually pick it up in an old-fashioned television set like your grandma may still have around the house. Question?
Can we go beyond that?
No. Or rather, we cannot go beyond that in this way. But people, various teams around the world are doing precise measurements of this to see if they can pick up the remains, the traces of events that happened earlier than this, like the BICEP 2 survey a few years ago that claimed that they had found polarization information in this from the inflationary epoch much earlier than this, in the first 10 to the minus 35th of a second. But they're wrong, because they did their sky subtraction incorrectly. But they're still at it, they're still funded, and they still have their telescope in Antarctica, and maybe they will do it right one of these days. So yeah, and of course, the Big Bang, of course, the obvious question is, well, what came before that? And the honest answer is we don't know. We have no information about this. But we probably can see much earlier than this. See traces of events earlier than this. It would need a more precise image than this one, though. But they are working on it. So the cosmic background radiation is a picture of the primordial fireball. This used to be visible light. Since then, the universe has expanded by a factor of 1,500. It's now thin simple microwaves. So we can see light from the universe when it was about 400,000 years old. Can't see before this quite yet, but there may be ways of doing it. Hubble Space Telescope has seen to about 13.6 billion years ago, out of the 13.8 billion year age of the universe. So Hubble Space Telescope has seen things, galaxies, as far back in time as 200 billion years after the Big Bang. The point is, currently there's this gap for which we have no light at all, from when the universe was about 500,000 years ago to about 200 billion years ago. And since we have detected no light at all from this early time, it's being called the cosmic dark age. The James Webb Space Telescope is designed specifically to look into this cosmic dark age. This was a scientific project that was selected to drive the technology. It will be used for other things, like observations of nearby star formation, but this was the one, this was the key project selected to drive the technology. So James Webb Space Telescope is designed to look into this cosmic dark age. The time between when the cosmic background radiation, the cosmic microwave background, was radiated and the oldest now visible light was radiated. This includes the birth of the very first ever stars, referred to as cosmic dawn. This includes the first heavy elements made by the nuclear processes in these stars. It is estimated we are made out of third or fourth generation material. The carbon, nitrogen, oxygen, and phosphorus making up the proteins in the flesh of your body, and the nucleic acids, and the calcium in your bones, and the iron and the hemoglobin that makes your blood red are thought to have been made in stars. And it's estimated that we are made of third or fourth generation material. So you are made of material that's been cycled through 2 or 3 generations of stars. This will observe the very earliest and work this out in detail. Also, the first star death, the first generation of stars, there were no metals, there were no heavy elements. The universe was only hydrogen and helium from the Big Bang. And so therefore, they were probably very short-lived and seeded the universe with heavy elements since then in explosions massive explosions called supernova explosions. So the first stars, the birth of the first stars. Hubble has gotten a few observations of the first generations of stars, but they're sketchy. This will be the first detailed observation of the first generation of stars. The birth of the first stars, the first heavy elements made of these stars, the first star death and supernova explosions, the first black holes blown into space by these supernova explosions, and the earliest protogalaxies coalescing by gravity out of the primordial chaos. Very heavy stuff. It also, James Webb Space Telescope also should observe star and planet formation nearby us in the local universe. Again, radiates infrared because it's warm. Roughly room temperature, a little warmer. Also, the atmosphere of planets of stars under the sun, referred to as exoplanets, that's been a big deal in the past 25 years or so, the discovery of stars around other stars, not extra planets of our solar system, but actual planets of other stars. There are now over 5,000 known, referred to as exoplanets. The very first science observations planned for James Webb Space Telescope are in fact spectra of the atmospheres of planets of other stars, of Earth-sized planets in the habitable zones of sun-like stars, where the temperature is between 0 and 100 degrees Celsius, so there might be liquid water and therefore life, and a search for life. It probably won't be able to do this for more than a few of them though, but if they get exceptionally lucky, or if life in the universe is common out there, that might be a very important press release for later this year. And of course, the nova shells and bow shot nebula that I observed. So I intend to write a proposal for this. I didn't bother with the first cycle because I knew that all the people who worked on this would be getting their guaranteed telescope time. So, but nevertheless, I intend cycle 2 or 3 to put in a proposal to observe the nova shells and bow shot nebulae that I have worked with. The 2000 decadal survey also recommended the Olmo ray in the Atacama Desert in Chile, where it has never rained in 500 years of recorded history. It's astonishing. And it was completed, the array was completed in 2013. It helped to make this direct image of a black hole in the center of the active galaxy M87. It was taken by the Event Horizon Telescope, the interferometer spanning across the globe from the South Pole to Chile, to Hawaii, to North America, to Europe. The black object inside the bright ring of gas is the size projected for the event horizon of a black hole of that expected mass. People nevertheless complain that the image is blurry. Remember Catherine Elder, graduated here, physics major, graduated here in 2016, went off to the PhD program at Arizona State, is currently putting together a radio telescope capable also of looking into the cosmic dark age. I told her, put a component, build me a radio telescope. The component's one of these on the far side of the moon, and link it in interferentially. Since the moon is 60 Earth radii away, you would improve the resolution of this image by a factor of 30. Therefore, being able to see the fine currents of gas going into the black hole and various general relativistic effects. So I told Catherine, don't risk your life doing it, get some robots. ALMA is the Atacama Large Millimeter Submillimeter Array. It took these images of planetary systems forming by gravity out of gas and dust, the interplay of gravity inwards and angular momentum outwards to form the planets around the stars in the middle. ALMA's combination of resolution, in other words, how clearly you can see, and sensitivity, in other words, how faint it can see, are together the highest of any telescope now available. Cost $1.3 billion. Yes, ground-based telescopes have now risen in price to be comparable to those of space telescopes. So joy and delight. The 2010 decadal survey recommended the Nancy Grace Rubin Telescope. This is not Nancy Grace, the Fox News crime reporter. This is Nancy Grace Rubin, NASA's first ever chief of astronomy, 1962. She is shown here with a model of orbiting solar observatory OSO-1, the very first space telescope. Back in those days, satellites were primitive. You had to spin the satellite to keep it from processing all over, to be able to transmit and receive radio signals from it. And the received wisdom of satellite builders of the era was, you can't point a science instrument in a direction because you have to have the rest of the satellite rotate to stabilize it. Well, Nancy Rubin and her team did not know this. So they had the idea, we put a hinge between the two parts of the telescope. So the top part, the satellite. So the top part has got an ultraviolet camera to look at the sun, and notice solar panels right in back, because we pointed at the sun, therefore generate electricity for the spacecraft, and the bottom part to rotate. It was also the first ever spacecraft, not just telescope. Well, it was the first telescope in space. The first ever spacecraft of any kind, not just telescope, capable of pointing an instrument in a specific direction, and the very first spacecraft with an onboard tape recorder, so it could take data even when it was out of radio contact with Earth. Nancy Rubin did not like to be called the mother of Hubble Space Telescope because, as she said, it was a team effort, and it takes credit away from the team. But to cry out loud, she recruited and hired every member of the team. She supervised them in the development of space telescopes. She did much of the work herself. She even lobbied Congress for funding. So the telescope, the Nancy Grace Rubin telescope, is planned for launch in 2027. It's similar in size to Hubble. It's got the same aperture Hubble, 2.4 meters. In other words, about the size of NASA's school bus. But its optics cover 100 times more area. Got a much wider field of view. So like that poster in my office of distant galaxies taken with Hubble, Nancy Grace Rubin telescope will be able to do that for the whole sky. And this is because it was originally designed and built by the National Security Agency as a spy satellite looking down at Earth, and they realized they would need it, so they gave it to NASA. NASA has another one in a warehouse that they don't have the budget to do much with, but this one they're going to launch in 2020. It is designed to observe supernovae, to map dark energy, thousands of supernovae, to map dark energy throughout the universe. It should also use gravitational microlensing to find over 100,000 exoplanets, about 5,000 are currently known. So that'll be a big deal. And Vera Rubin Observatory, 2000 Decadal Survey recommended Nancy Grace Rubin Telescope, and the Vera Rubin Observatory in Chile. Both of them are wide field telescopes, capable of observing large areas of the sky, and so both of them will be gushing torrents of data. Therefore, all the young astronomers these days are learning data science and machine learning to be able to cope with this. Vera Rubin Observatory first lies planned for just a couple years from now, 2024. You can see it under construction on Cerro Machón in Chile. There's the Gemini 8-meter telescope. It's designed to map dark matter, not dark energy, but dark matter throughout the universe by observing the entire southern sky, 350 times fainter than the Catalina survey that Chance Spencer is writing his thesis using data from, and other students that I have used, in 6 colors as opposed to 1 color for Catalina, twice a week as opposed to once every week and a half, so 3 times the higher cadence for 10 years, like the Catalina survey, with enough resolution to be able to see a golf ball on Earth from space. When writing this, I originally phrased this as a golf ball from Earth orbit. I never realized there's 2 golf balls left on the moon by Alan Shepard. So, no. A golf ball on Earth from space, yeah. Vera Rubin discovered dark matter in 1976 with the 4-meter telescope at Kitt Peak, and also the 2-meter. She was nominated for a Nobel Prize for it. Sadly, since she has died, she'll never collect it. I had the great honor of being fed chicken soup when coming down with a head cold in the Kitt Peak dining hall by her. The magnitude of the honor was not lost on me. I said, and as she said in 2002, I said in 1980 that we know what dark matter was in 10 years, but the part of physics would tell us. Well, they have not. Nor has dark matter, nor dark energy have either of them been predicted by any theory, such as string theory. And the thing is, dark energy is supposed to be 70% of the universe, and dark matter is supposed to be 23% of the universe. Ordinary baryonic matter, made of atoms like we're made of, is less than 5% of the universe. So this, we look out in the universe, it's like looking into a dark ocean. All that we're seeing is the white caps on the waves of the water on the surface. A big, dark, mysterious ocean underneath us. We don't know what's going to happen. It's probably something big, probably comparable to the Michelson-Morley experiment. Something seriously going wrong in our understanding of the basics of the universe, like the Michelson-Morley experiment was, starting in 1881. A generation later, of course, a young patent clerk by the name of Einstein would figure it out. The 2020 decadal survey considered a new generation of great observatories in space. HABEX, or Earth-like exoplanets, 4-meter telescope with a star shade, because the sun is 3 billion times brighter than Jupiter, so it would be difficult to see Jupiter if you're looking at the sun. It's a star shade. And the large ultraviolet optical infrared surveyor called LUBAR, basically a super Hubble Space Telescope, basically like Hubble Space Telescope, a true replacement for Hubble Space Telescope, but much larger, 8 to 15 meters in aperture. Lynx for X-rays, a super Chandra X-ray observatory. Chandra is now over 20 years old, it's getting old. And Origins for mid and far infrared, a super Spitzer Space Telescope. Spitzer died in 2020. So Astro 2020 recommended a compromise between the 4-meter HABEX and the 8 to 15 meter LUVOIR, and at least 6-meter aperture LUVOIR B, optionally with a star shade. Whether the star shade will happen or not depends on budget and also whether it will really be necessary. It will be cost capped at $11 billion because of the way the costs get out of control with James Webb Space Telescope and Hubble for it. James Webb Space Telescope was proposed in 2000, initially for $3 billion, scheduled to be flying in 2007. It finally flew in 2021, 14 years late, at a cost of $10 billion, $7 billion over budget. We're not going to be able to do this again. Who do astronomers think they are? The military? Therefore, this will be cost capped. If they can't do this for $11 billion, it won't happen. It is planned to launch in 2045. I will be 86 years old, old joy and delight. Its key project will be to observe between 20 and 50 Earth-sized planets in the habitable zones of sun-like stars, well enough to detect the presence of life in any of them and measure, therefore, the prevalence of life in the local universe. Lynx and Origin are planned for the mid-2030s at a cost of $3 to $5 billion each. And also recommended for ground-based astronomy are the nearly 25-meter Giant Magellan Telescope that was in Chile, planned for 2029. Again, yet another reason why Spanish is a great language for astronomers to know. Chile is really a wonderful site. And all the good stuff in the southern hemisphere, you know. And the 30-meter telescope in either Hawaii or La Palma, Canary Islands, planned for 2027. Why they're having problems with the people in the local community protesting that they don't want any more building up on the top of their tallest volcano, Mauna Kea. La Palma is a wonderful site where most of the European observers are. It's in the Canary Islands off the Sahara Desert in Spain. Actually, it belongs to Spain, but it's off the coast of the Sahara Desert in Africa. Problem is that the volcano in La Palma, it's a little volcanic rock sticking out of the ocean, similar to Hawaii, great astronomical site. Problem is, late last year, the volcano became active. And so volcanic eruption may be 15 kilometers away from the observatory. And the observatory is at the edge of a large, thought to be extinct caldera. And when I observed there, when I was postdoc in England, I went down there. And I've been living in England for a couple of years, so I learned some of the language. And I asked, is it a bit adapt to put a major observatory at the edge of volcanic caldera? And the Australian staff member said, oh, no worries, mate. The last eruption was in 1971. on the other end of this 10-mile long island. And I did not find that reassuring, so I don't know. The decadal survey has also recommended that the two projects be merged together, probably to be in the southern hemisphere. So, and you may wonder, well, how this key project for UVRB, how exactly do you measure the presence of life in the local universe? So how do you detect life on distant planets? The answer is get spectra of their atmospheres. This is why the very first science operation scheduled for James Webb Space Telescope is doing this, just in case they get lucky, or just in case at least bacterial life, simple life, is present just about everywhere in the universe. It did evolve on Earth. More than 90% of the time, there has been life on Earth. More than 90% of the time, the Earth has been cool enough to support life. So maybe that's telling us that life forms easily in the universe. But it's awfully difficult to do statistics with a sample size of 1. So we don't know. Unlike Venus and Mars, Earth's atmosphere is full of oxygen. Earth's atmosphere is 21% oxygen because of the presence of light. It's highly oxidizing, therefore very much out of chemical equilibrium. So we get spectra of the atmospheres of these planets, you and find gases that are greatly out of chemical equilibrium, such as molecular oxygen, or ozone, or methane, or anything else. That would be a pretty good indication. That's thought to be a pretty good indication of the presence of life, at least bacterial life. Intelligent life may be a lot harder to find. Have you noticed it's rather difficult to find on Earth? And of course, word of advice to the students, never give a science fiction talk. Always show some results that you have done, not only on what you're going to do. The rest of the talk will be about astronomy at Fresno State during the next 2 years. Fresno State Physics is a vigorous astronomy program with our campus observatory, and these are not my students. Fresno State Station at Vera Rubin Observatories, our projects with the Hubble Space Telescope, other NASA spacecraft, and observatories near worldwide. Students are welcome to participate in hands-on research on exoplanets, cataclysmic variables, flare stars, starburst galaxies, quasars, and, of course, black holes. I will offer these 100-level astronomy and astrophysics course next academic year. Both will require physics 4C as a prerequisite. In the fall, the observational astronomy course, largely in the campus observatory, to teach students how to take these beautiful images, all taken with this telescope. Show me a student who could take images this real good, and I will show you a student who taking any kind of science data will seem easy. And also in the spring, the bad weather time of year, well, that's when you have the theory course, the Physics 150 Astrophysics, requiring Physics 4C, and with all the math and great fun. And I also intend to teach the Physics 175T Orbital Mechanics and Spaceflight course in fall of 2023, alternating it every other year with the observational astronomy course. My Fresno State Telescope at Vera Rubin Observatories is now fully operational again. My thanks to graduate students Chance Spencer and Armando Guerrero for helping me over the summer get it back into shape. My students have operated mostly from one campus over the internet, although we do go up there every now and then. And this one is it. This is Observatory 7, the first of the original 8. Since then, there's been substantial additions to this. This is Vera Rubin Observatory. This is not all these telescopes belong to us, just this one. Don't I wish?
Where is this place?
What?
Where are those?
It's about 4 miles away from Shaver Lake. It almost burned up in the campfire. Yeah, it was scary, but it's okay now. It's an altitude of 4,910 feet, high enough to get a really nice, beautiful dark sky. The Milky Way is easily visible on the occasional satellite that goes by. Beautiful dark sky. And it now has a proper dorm with a proper shower and a proper bathroom. That's, for many years it was designed as a robotic facility. We don't have these things. And they're mainly roll-off routes. Roll-off routes are more reliable, mechanically simpler, and easier to maintain than the traditional observatory shelf, like the campus observatory on campus. So usually I start students out observing the physics 151 observation astronomy class, and then involved them in research, moved them to taking observations with this, mostly from campus over the internet, because it's 40 miles each way, 41 miles each way, so driving up and down gets old after a while, especially in the freezing cold winter. Chance Spencer is currently finishing up his MS thesis on black hole and neutron star binaries and old Delphi from the automated Cantilever real-time transit survey, one of the precursor automated surveys, precursors for the Vera Rubin Observatory, accretion onto a black hole or a neutron star. Armando Barrero is writing his thesis to finish up in December, are superflares of sun-like stars caused by magnetized planets. Armando has basically convincingly shown that the answer is probably no. But the reason why these superflares, millions of times more powerful than solar flares, happen on stars apparently similar to the sun, Armando has found is because these stars are not similar to the sun. Therefore, we don't need to worry that the sun will do this. Because if it did, it would probably fly every electronic device on Earth. Two new students. Saurabh Karat is starting a program on the phenomenon of flickering, as you have accretion onto a white dwarf, burnout cinder that used to be a star from a normal star. It erratically flickers, and all accretion disks, and star formation, and galaxy centers, and so forth, they all erratically flicker like this. And we don't know why. It's the easiest kind of variability to observe these things, and it has yielded the least amount of physics. It may be magnetic reconnection similar to solar flares, but we don't really know, and we would like to make some progress on this, at least get some good observations and novel methods of statistically analyzing, for example, using fractal geometry, self-organized criticality, to look at these erratic light curves. Calculus is good for looking at things that vary smoothly, like laminar flow. It's not so good for looking at turbulent, discontinuous phenomena. And that's what this is. And the new mathematics does exist.
What new mathematics are you talking
Fractal geometry.
about? Oh,
Benoit Mandelbrot. Mandelbrot famous quote from Mandelbrot is, remember physics 4A, all those simplifying assumptions? The Hookean perfectly elastic spring connected to a massless string draped over a frictionless pulley attached to a point mass on a frictionless surface. And don't forget to neglect air resistance. That this works as well as it does is a tribute to Isaac Newton's genius. He knew what to ignore safely. But remember those stupid frictionless hockey pucks in the physics 4A lab that are never frictionless enough. There are limits to my patience with this. As Mandelbrot said, clouds are not spheres, neither are cows. Cows are not spheres, nor are they cylinders. Mandelbrot said, clouds are not spheres. Oh, come on. Mountains are not cones. Tree bark is not smooth, nor does lightning travel in a straight line. Many phenomena in nature are irregular and nonlinear and crinkly like this. And only now are we getting mathematics capable of analyzing it. And as far as I can tell in the literature, nobody has tried this before. It's a really good project. Also, the Peter Martin was working on the origin of cataclysmic variable. Where do these close binary star systems come from? It's not that they're initially wide apart, far apart, and that one of the stars, the star that makes the white dwarf, will first swell up as a red giant and engulf the secondary star. This is probably a very violent, messy process, and very short-lived, which is why there isn't a star in the sky that we can point a finger at and say that is common in world evolution happening right now. And basically, we'll strip roughly 90% of the envelope's mass off and roughly 99% of the angular momentum lost to space, giving you a short period binary. The point is that when the first paper that was written about this was published in 1906, it was published on the basis of observations of 22 of these close binary star systems, of which 7 were high-quality data. Now we have easy access to 619 data on 619 of these objects, about, I would estimate, 40 to 50 of which would be high-quality data. So a nice, well-defined thing for Peter to answer first is, are the conclusions of Hans Schroeder's 1986 paper still valid in the context of this much larger and higher quality data set we have now? And just in case anybody is wondering, I've written up a slide on the human spaceflight program, which of course has relatively little to do with astronomy, but of course that's the one that everybody cares about. Let me stop there for now.
Okay, questions?
So what kind of fractal geometry is using electron? What kind of fractal geometry? Statistical?
I did give a little bit about this. I should give another specifically about fractals. The point is, one of the basics of fractal geometry is the notion of fractal dimensions.
Yeah.
That, okay, we think we know what a one-dimensional thing is. We think we know what a two-dimensional thing is. We think we know what a three-dimensional thing is. And so forth. So 1D, 2D, 3D.
It's simple to calculate fractal dimensions.
Yes, yes. The point is, fractal dimensions are dimensions in between
That's why they
that measure how rough a surface is. One of them, one of the most famous early papers about this, had the title, published in Science, and had the title, How Long Is the Coastline of Britain? Because it was pointed out that if you look at different atlases, they give you different answers, because it measures, it depends on how long your ruler is. If you use a really long ruler, you get a shorter coastline, because it's short, the coastline of Britain is critical. In other words, it has a height, it has a fractal dimension close to 2. Whereas the coast of South Africa is on the edge of a big cliff, maybe escarpment. It is a crinkle. So it has a fractal dimension close to 1. And, for example, totally uncorrelated white noise has a fractal dimension. If you plot, say, intensity, so it's a function of time. Yeah? What's the...
stock market have a fractal dimension?
What did you say?
The stock market.
Yes, the light curves. What we want to do is measure the light curves of the stars, these plots. Take a bunch of them, different stars under different circumstances. These are called cataclysmic variables because they have outbursts. So both in quiescence, in between the outbursts, and during the outbursts. And see, does the roughness of these curves, do the fractal geometries change as a function of luminosity, power output, in other words, outburst state. Is this related to what you see in stellar magnetism, in solar flares, for example? Solar flares have a fractal. Solar flares have a power law distribution because of the fractal geometry of the field lines in the flares. The field lines get stretched because the sun rotates differentially. It doesn't rotate like a rigid body, therefore the field lines get stretched until finally they break and release a great deal of energy, and that is a solar flare. So, does the mathematics of this, does the fractal geometry of this, the fractal dimensions of this, resemble that of solar flares? So therefore, can we make a link?
Calculate the fractal dimension of that?
Yes. Tell you what, that is actually, do I have, because that is the whole science of how to calculate fractal dimensions is very much material for a whole talk. Do I have? What?
You should keep it talking.
I should. And the thing is, I think I have the slides. I think I have the slides for it right now because I've done this. Let's see. Nonlinear astrophysics at Fresno State. I did give a talk on this a while ago. Here we go.
Wait, Fred, it's not showing up on this screen.
It's not showing up on the screen. Start with this one and do this. There we go. I should make, when I do give this talk, I should give it a better graphic. The point is, how does this mathematics connect with physics? If you have a situation like we study in those physics courses where everything is linear, and therefore laminar flow in hydrodynamics, and therefore not measured by fractals. Basically, you have a situation where you have whatever you're studying has a typical size scale. For example, how tall people are is constrained by physics and biology. Your average American woman is 5'4" tall. There are very, very few more than twice as tall, and very, very few less than half as tall. So the distribution of heights, number of features of different size, is you can quantify with a normal distribution, a Gaussian distribution, the old bell curve, Gaussian or normal distributors. For things that are described by fractals, you have many sizes over a wide variety of ranges and relatively unconstrained by physics. For example, how wealthy people are. One of the fundamental things about economics is that you can be twice as smart as somebody else, but you can be tens of thousands or millions of times richer than somebody else. It's relatively unconstrained. So therefore, the number of features of a relatively unconstrained situation does not fit a Gaussian distribution, a normal distribution. It fits a parallel distribution. Earthquakes are an example. Big powerful earthquakes are quite rare. Little, not so powerful earthquakes are very, very common. This isn't just physics. This is biology and also the social sciences. For example, big cities are rare, little ones are common. Big traffic jams are rare, little ones are common. Big stock market fluctuations are rare, little ones are common. Well, big fluctuations in the flickering light curve are cataclysmic. We'd like to find out how common or rare they are in proportion to that. So, self-organized critical systems have parallel distributions where there is no correlation at all. That's pure white noise. So the size of each fluctuation as a function of frequency is independent. Therefore, it's perfectly white noise. But that's not what the flickering light curve of a cataclysmic variable looks like. Of an accretion looks like. It's got more power at low frequencies, what's called peak noise. And others, for example, Lisa Lee did a thesis last year on the light curves of active galaxies, quasars, and she discovered they are dominated, that the flickering in them is dominated much more by low frequency noise, brown noise. Did you ever see the launch of a large rocket? Say at Kennedy Space Center? It's a sound, it is a truly unearthly sound. It is a sound much more felt than heard. Yes, it is very, very loud, but most of the sound is at frequencies too deep for the human ear to hear. However, first law of thermodynamics, of course, says that energy doesn't go away. That energy is still there. You feel it. You feel it in the air, and you feel it in the shaking of the ground, and you feel like you're being punched in the chest. At the same time, a slap in the face. It's great fun. So therefore, a big, and you might think, okay, a big black hole might make a light curve dominated by low frequency noise. A little one might make a light curve dominated not so much by low frequency noise. And so basically, a good thesis for start off to do would be get a bunch of light curves of these, get observations of these, and measure these fractal dimensions. Plot them up, measure the power loss, and see if we can find any correlation between size of the star and luminosity, power output of the star, whether it's the power, whether the fractal dimension, the power loss slope is lower in outburst, for example, than in quiescence. And if we can find that, establish that in a systematic way. Our searching through the literature has indicated nobody has tried this before, so it'll probably be a big deal. But that wasn't difficult to do because only about 9 or 10 papers about this phenomenon have ever been published.
Well, the difficulty comes from measuring the stars accurately enough.
What'd you say?
The difficulty comes from measuring the stars accurately enough.
No, that's boring, actually. We know how to do that. You put the telescope at the star, take a series of images, let it run all night, optimally while the observer is awake. In case the weather gets bad, you need to close the telescope. We haven't completely automated it yet. And that would be a nice thing to do. And just let it track and get a series of observations all night. At the end of the night, close the telescope down, close the housing, observatory housing. We have software that can automatically measure how bright a star is. The same star is in the series of images built in other stars that field carefully chosen so that they do not change in brightness. And therefore, measuring light curve is easy. And measuring the power loss slope is easy. Just copy and paste it into an Excel spreadsheet, hit the sort function, give you the sorted list, plot it up, do a linear fit, measure the slope. So, actually pretty easy once you realize what you need to do. Anyway.
Just to keep, so not
And
let us ask questions. So let's take maybe one more question, if there is another question. And if you want to talk to Dr. Ringwald afterwards, there's plenty of time. So one, Paul.
Paul.
There's a big Starship out there. And Starship, if they get it to work, it should make the volume and weight of payloads much greater than what.
Oh, NASA is.
100 times. And then the cost would if they get it to work, if they get it, but.
Okay, that's my last slide, What?
Are astronomers looking at that carefully, or will that revolutionize what kind of space telescopes you can?
Well,
Or is it not as big a deal?
considering the impact of the Starlink satellites, I don't think Elon Musk's priorities, I don't think astronomy is a very high priority for Elon Musk, considering. But yeah, the Starship. The one that NASA, the heavy lift vehicle that NASA is currently developing. Again, NASA is developing the Space Launch System, SLS, heavy lift rocket, and the Orion multi-purpose crew vehicle, picture shown here. Robotic test flight is scheduled for later this year. It's supposed to be February, then March, then April, now May, no earlier than May. Current plans are to fly astronauts around the moon in 2024, to land astronauts on the moon by 2025, although, frankly, this is doubtful. It will probably at least slip into 2026, the first landing by astronauts on the moon since 1972. And on Mars in the mid-2030s. China's third station, Tianlong, launched in 2021. Crew of 3 is now aboard. China wants to land humans on the moon by 2030. The next big land grab. You may have noticed that the war in Ukraine, who does Vladimir Putin think he is? Peter the Great? It's the kind of thing that you would do in the 700s. Well, history has a nasty way of repeating itself. The next big land grab may be for the South Pole of the Moon, because there is ice there, making it a lot easier to live on and mine the moon, and would revolutionize the economics of spaceflight further into the solar system to mine things like platinum. So, yeah, so notice how these dates get closer and closer to each other. NASA retired the space shuttle in 2011, and plans to retire the International Space Station in 2030. Probably will do that earlier because the Russians are getting very huffy about their maintaining their parts on it because of the war in Ukraine. Commercial rockets by Elon Musk's company, SpaceX began flying astronauts to the International Space Station in 2020. NASA's awarded contractors for one or more commercial space stations they've awarded 3 different contracts. None of them were to SpaceX. One of them was to, I think, Bigelow, the other one was to Northrop Grumman, and the third one was, I think, Axios. For commercial space stations, replacing the International Space Station after 2030. SpaceX says they want to send humans around the moon in 2030 on their Starship. But Starship has blown up twice. So whether or not this will happen, we don't know. We still don't have driverless cars yet, do we? So, yeah, it's very iffy. But it is certainly true that people at NASA are shitting bricks. Because Space Launch System is designed with relatively old technology. RS-25 space shuttle engines developed in the late 70s, and solid rocket boosters developed also in the late 70s. Estimated to be between $2 or actually more honestly $4 billion a flight. Starship is designed to be totally reusable. And assuming that you would not have to do a significant amount of maintenance between flights, which is a big assumption, assuming that the only cost to fly Starship is the fuel, would cost as little as $2 million per flight. You may remember, since the 1960s, we've been pursuing this much touted factor 10 reduction in launch costs. This could be a factor of 1,000. So, if you want to know what's going to happen, I can't tell you. Things are happening.
Well, on that note, let's thank Dr. Ringwald for the great